Physics currently struggles with two distinct anomalies at absolute opposite ends of reality. At the macroscopic scale, cosmological models require dark energy to account for the accelerating expansion of the universe at the cosmic horizon. Dark energy is a hypothetical, invisible form of energy proposed to explain why this cosmic expansion is speeding up rather than slowing down. At the microscopic scale, we lack a defined physical mechanism for objective wave function collapse in bound quantum systems. Wave function collapse is the process by which a quantum system, initially existing in a superposition of several possible states, strictly reduces to a single measurable state upon observation. Historically, researchers have treated these as two entirely separate problems. This division exists because the mathematics used to model both phenomena rely exclusively on three-dimensional volumetric or bulk dynamics. By relying on these 3D bulk parameters, physics has built incompatible explanatory structures for the largest and smallest scales of the universe. The gravitational math of the cosmos does not speak to the probabilistic math of the quantum realm. This suggests that the failure to unite these anomalies is not due to a lack of data, but a consequence of modeling them at the wrong geometric level. Independent researcher Nadav Bashan proposes an alternative framework. He examines whether the relevant physical laws governing these phenomena are not volumetric at all, but strictly boundary-based. The core mechanism of this framework redefines how we look at data. Instead of analyzing an internal 3D volumetric process, information transfer is treated as a two-dimensional boundary-crossing event. Through this single lens, both the macroscopic limit, where the cosmic boundary reaches horizon-scale saturation, and the microscopic limit of radiative extraction from a single atom can be calculated using the exact same geometry. If a single boundary relation accurately reproduces both kinematic structures, then cosmological expansion and quantum collapse are distinct physical regimes governed by the exact same geometric law. To test this hypothesis, we must transition our mathematical focus away from the volumetric parameters of the bulk and isolate the kinematics of the boundary. Calculating a boundary crossing event requires four specific variables: the characteristic boundary scale, denoted as r, the transition frequency, omega, the causal limit set by the speed of light, c, and a dimensionless transmission efficiency parameter, epsilon. These variables form a scale-invariant master equation for boundary transmission. The critical piece of this formula is the kinematic monomial at the end, r squared times omega cubed over c squared. This specific kinematic monomial is the structural foundation of the entire theory. We can prove its validity using dimensional analysis, a method of checking equations by evaluating only their base units. The monomial's dimensions are length squared times time to the negative 3, divided by length squared times time to the negative 2. This mathematically cancels out to time to the negative 1. Because time to the negative 1 perfectly describes a physical rate, the foundational law of boundary transmission requires no independent mass or temperature units to function. It is purely geometric. We begin testing this framework by projecting the boundary law onto the observable universe. We establish operational identifications for the cosmos. The boundary radius r becomes the Hubble radius. The transition frequency, omega, becomes the Hubble parameter, a value that describes the rate of the universe's expansion. Finally, we assume the macroscopic efficiency reaches absolute saturation, setting epsilon to 1. Substituting these horizon quantities into the master equation allows us to expand the frequency term. The variables cancel each other, causing the math to collapse into a simplified macroscopic boundary rate. The rate equals pi cubed over 15 times the Hubble parameter. In this boundary-based projection, variables for mass and gravity are no longer present. Projecting horizon kinematics to the surface causes the explicit dependence on bulk mass and Newton's constant to strictly cancel out. We now shift focus to the microscopic limit to test if a single radiative quantum transition obeys the exact same mathematical boundary structure. For the microscale, the boundary radius becomes the radiative decoupling scale of the atom. The temporal scale of the event is set by the emitted photon frequency. We operationally assign an effective kinematic temperature, which utilizes the Boltzmann constant, a factor relating average kinetic energy to temperature. We also define the single emission luminosity. We then substitute these intermediate descriptions into the reduced boundary invariant, creating a multivariable fraction. Notice the presence of standard quantum parameters scattered throughout the resulting equation. As we simplify, the Boltzmann constant cancels exactly between the numerator and denominator. Planck's constant cancels identically as well. We reduce the remaining frequency dependence to reveal the final microscopic boundary rate. The exact same kinematic monomial we found at the cosmic scale emerges completely intact. The implications are precise. Planck's and Boltzmann's constants govern the internal 3D bulk mechanics, but at the exact 2D decoupling surface, they vanish. The quantum state is governed by the same external boundary geometry as the cosmos. How does this theoretical mathematical ceiling compare to reality? We can test it against the realized spontaneous emission rate established in quantum electrodynamics, or QED, which is the relativistic quantum field theory of electromagnetism. We recast the standard QED transition probability into a parametric form using the fine structure constant. The fine structure constant is a fundamental physical value characterizing the strength of the electromagnetic interaction between charged particles. Comparing the established QED emission rate to the theoretical boundary law reveals an exact mathematical correspondence in the kinematic monomial. Both equations share identical spatial and frequency scaling. The only distinction between the two is the dimensionless prefactor. By isolating these prefactors, we define the mathematical ratio between the specific, realized QED rate and the absolute geometric ceiling of the boundary. This forces an operational reinterpretation. The fine structure constant operates as part of a dimensionless emissivity factor. It dictates exactly how efficiently a bound quantum state externalizes its information compared to the absolute physical limits of its 2D geometry. This chart plots kinematic boundary scale against transition rate. The solid line is the theoretical ceiling. The dashed line is the realized rate, lowered by the QED prefactor and fine structure constant. Microscopic limits land on the extreme left, macroscopic horizon limits on the extreme right. Despite operating at opposite ends of physical reality, both the cosmos and the quantum state sit perfectly on lines of identical geometric slope. They are separated strictly by their transmission efficiency. This table summarizes the distinct division of variables under this framework. Surviving boundary variables dictate kinematics. The traditional constants of gravity and quantum mechanics are relegated to intermediate descriptions. The bulk constants are not false. They belong to the internal description of 3D volumetric dynamics, not the external transmission mechanics of a 2D boundary. Bashan presents this as a strictly falsifiable research program. It fails if future transition evaluations don't systematically cluster near this specific geometric boundary ceiling, or if the cancellation of bulk parameters relies on inconsistent identifications. If validated by further mapping, cosmic expansion and wave function collapse are no longer disparate, incompatible anomalies. They represent distinct regimes of a single unifying geometric boundary.